Hi, everyone. So I'm obviously not Hugh. He's out of town. So I'm taking on the role of moderating today's speaker. I have the pleasure of introducing Dr. Sharanya Majumdar. He's a professor of atmospheric science at the University of Miami. He's also the reason y'all have to put up with me because he was my PhD advisor. So he can apologize to you separately for that. And so he and his research group investigate tropical cyclone predictability, including genesis, intensification, structure. He has a rich background in data assimilation and also has done some work with risk communication, which was really interesting. He's also developed courses on predictability and tropical meteorology, served in the graduate school administration. Actually started that when you were still in that or just got out of that when I joined. And he also spearheaded the development of a new Climate Resilience Institute at University of Miami. So that's a really cool thing if you want to chat with him afterwards. A lot of really cool stuff happening there. And finally, he's also a visiting scientist at ECMWF and a recent fellow of the American Meteorological Society. He's going to be talking about developments at ECMWF and Atlantic tropical wave and cyclogenesis forecasting. So Sharan, I'll let you take it away and turn on the mic. Right.
All right, thank you very much, Quentin, for the very gracious introduction. And yeah, it's just been awesome over the career to have terrific students such as yourself, and so glad to see you doing so well here at NCAR and keeping everybody on their toes. So I'm going to wear my ECMWF visiting scientist hat here a bit and just talk about some developments at the center and then how that relates to tropical wave and cyclogenesis forecasting. So I'd like to acknowledge Quentin and a lot of my collaborators at ECMWF who were instrumental in this study. I actually spent a year at ECMWF right in the middle of the pandemic, so I was like 3 miles away from the building and just sitting on a couch writing lots of code. I actually wanted to write code, so it was a good time professionally, even though it's a little bit weird for a whole year of my life doing that. But anyway, it's borne some dividends. There's a couple of papers that were published on the 4-kilometer global model that was run at ECMWF, still hydrostatic. So that was published in 2023. And then in 2025, a paper led by Linus Magnusson looked at a lot of data assimilation experiments with different types of satellite and aircraft data, but still focusing on tropical cyclones as the verification metric. So that was published in Quarterly Journal in January. And then this is the third major study, but it's hopefully ready to be submitted a few weeks or months from now. So let's get going. So I'll first give an introduction to the ECMWF forecasting systems and just a fairly sort of broad overview of their AI forecast systems. But I'm not an AI expert, so I'm not going to get way in depth into the algorithms. And then we'll switch to tropical cyclogenesis and talk about some of the ensemble predictions, largely with the operational system, and then a little bit of wave tracking in the regular operational system and the AI forecasting system. So we'll first start with the ECMWF for forecasting systems. So the cycle during the last two hurricane seasons was called 48R1, and it's a 9-kilometer control forecast. So there's no sort of deterministic forecast anymore. It's just an unperturbed forecast and then 50 perturbed members. So it's essentially a 51-member ensemble. And then there have been a few upgrades, as they always do each year. And so for this current hurricane season, there are a few improvements here. A couple that are related to sort of land surface observations and models. Then a little bit in the ensemble of data assimilations that helps initialize ensemble and provide an improved covariance structure. And then the last one's actually a big one here is that they've changed their model physics perturbation scheme. So you've probably heard of the SCEB scheme. I think some of that was developed here. And then also they previously had stochastically perturbed tendencies, but now they just stochastically perturb the parameterizations, and that's their representation of model uncertainty. So with the AIFS, which of course is a lot newer, it became operational from February the 25th this year. And you can download the code. I think some of you have. I know Quentin has. And of course the forecast data too. Importantly, it still just uses the same initial conditions as the operational IFS or integrated forecasting system. It's just initialized off the 4D VAR analyses, and then we get 4 forecasts per day. The grid spacing is about 28 kilometers. So they've just recently done the whole retraining on that finer resolution. So how it's designed is based on a graph neural network. And so it has the encoder, processor, and decoder framework like this. So one takes the inputs, and then the encoder essentially just sort of assigns sort of on a coarser grid, just kind of these sort of local neighboring grid points, and then starts to work through the machine learning algorithm on this sort of coarser grid. And then the processor is what's known as a sliding window transformer. So this sort of takes advantage a little bit of the locality here, and it's sort of locality sort of vertically as well as sort of horizontally, and then it's done sort of within these bands in the transformer. And then that's all sort of put then into the decoder and then the output. So it goes through sort of standard neural network sort of training to then systematically improve on the weights. So there's a pre-training that's done on the ERA5 data set from 1979 to 2022, trained on 6-hour forecasts. And then there's sort of a finer tuning of the training that's done on the operational real-time IFS analyses from 2016 to 2022. So training's done in successive forecasts, kind of in 6-hour intervals out to 72 hours, using something that's known as an auto-regressive model that predicts the next value in the sequence based on the previous values. The loss function here is just the basic mean squared error. What the loss function means is that it's the computation of the margin of error between the AI model and a target value, which could be the analysis or the reanalysis. So that's used to guide the learning process and then keep updating the model parameters to iteratively reduce the loss function. So how does it do? Well, ECMWF has a scorecard of a zillion different metrics, which I won't show. But as you've probably seen in press releases from them and many other sort of private sector companies as well, that the AI systems, at least for synoptic type metrics, tend to do quite well compared with the physics-based models. This is true for tropical cyclone track, which is the figure right here, where especially from about 3 days onwards, one's starting to see some improvements in the track forecast in the AIFS compared with the IFS. However, it's pretty terrible for central pressure errors, and it's sort of biased very weak. So it's not as if the AI forecast systems are sort of ready to handle convective or mesoscale processes all that effectively yet. Another advantage is that it's much faster than a forward numerical prediction. Of course, there are limitations. I could talk about limitations for a long time, but here are just a couple of them. So with that loss function of the mean square error, what that means is that it actually penalizes where you have a forecast for a feature that could be predicted correctly, but is in the wrong position. So you get this sort of double penalty. So the mean square error actually would better reward this forecast of just a blurry feature, as opposed to one that is a more accurate feature, but in the wrong place. So that can cause some problems, especially at longer lead times, with creating some more blurry fields. Also, it doesn't reproduce the energy spectra that the physical models have, and it doesn't completely represent the dynamically balanced relationships. I did look a little bit at thermal wind balance in hurricanes, and it's not terrible, but of course pressure gradients are very weak. So ECMWF also is currently developing AI-based ensembles. So these are not operational yet, but they're looking to make this operational hopefully this fall. And so the motivation, of course, is fairly clear that we want to reduce biases by training on historical data and then efficiently computing perhaps 1,000 ensemble members as opposed to 50 every 6 hours. So they've had a couple of iterations using the diffusion models or just sort of ensembles of the single AI system. What they seem to be converging on is what's called AIFS CRPS. Sorry, that's a bit of a mouthful. And so it uses a loss function that's somewhat based on the this particular formula here, the CRPS. And it's actually a slightly tweaked version of this. And so what this does is it sort of balances out the distances between the ensemble members and the observations, which are Y, and the distances between the ensemble members themselves. And so just a schematic of that is that one takes a limited number of ensemble initial conditions and then runs it through the encoder, processor, decoder machinery on the GPUs, gathers all that together and then computes that CRPS loss. And then the sort of retraining over and over again is done with that loss until that loss sort of starts to asymptote. So they've been doing that training and they feel that they're almost ready to create an operational system out of this. I mean, this still seems a lot like magic to me, and I'm not sure I sort of follow the details of how this works. So there's no sort of physics parameterization changes and things like that in here. So onto the cyclogenesis part. So we'll just talk about the ensembles, mostly operational, and then a little about the experimental AIFS ensemble. So currently in National Hurricane Center operations, you see on the front page of their website, these probabilities. Here's a high, medium, low chance of a tropical cyclone existing within that region. And so those are estimated partly through forecaster intuition and also through this logistic regression tool that's developed by Dan Halpern, Bob Hart, and others. What's been done less is just the ensemble forecast probabilities and their evolution. Ryan Torn and I did this over a decade ago, and you found some promise and also some substantial caveats, which I think actually hold to this very day in some underdispersiveness or bias in ensembles. But then a more recent evaluation of the probabilities was conducted by David Richardson at ECMWF. So I'm very glad that he did that because I don't have to now, especially as my code's all in Fortran and I don't really want to convert it all. But anyway, his paper's out in Weather and Forecasting, that it's available online right now. And actually some of my findings are somewhat similar to his, but what he really focused on also was this issue of run-to-run consistency, or sometimes the lack thereof. He did a more formal evaluation. I'll emphasize that this talk is not really about an evaluation. It's just sort of trying to provide some idea of sort of where we are with the range of probabilistic forecasts, and then how that varies sort of depending on sort of the region, the version of the model, and so on. So we really focus on 0 to 10-day ensemble forecasts. That I'll just show an illustration from the IFS ensembles, where we'll look through the forecast of 10 to 0 days just for one case, which turned into a pretty destructive hurricane, Ian. Then we'll look at some sort of summaries of the probabilities over the last 5 seasons accumulated, identify some cases that we call low probability cases, which really is a springboard to my future research more than what I've done now. It was kind of like the money figure in the NSF proposal. And then look at a couple of other things, the waves versus non-waves, and then the impact of the resolution increase. And then we'll look at a little in the experimental AIFS ensemble. All of this part of the talk uses the operational cyclone tracker at ECMWF that was developed by Frederick Vitart and others back in the 1990s. And so that uses the vorticity. It looks for sort of a warm core anomaly. It looks at the minimum sea level pressure and looks at values of each of those that exceed some threshold. One point about our verification is that we don't actually verify on genesis, that we try and give the ensembles a little bit of a chance. And so we decided to verify on when the storm was named. That genesis has quite a few errors just in, or uncertainties in when it's actually declared as well. So I'd rather go for something just a little bit more robust. So this is just for when it becomes a named tropical storm. And then we have a distance tolerance, and then we'll talk about the maximum wind speed threshold, which is actually a very major issue here. So just looking qualitatively at some of the maps, so don't worry about all of the different types of shading and contours on the top. That we were doing this for field experiments each year, and everybody wanted everything overlaid, so there we are. So what this is a just a 0-day forecast, ensemble forecast, of what became Ian, so all ensemble members on top of each other right here. And this is just the corresponding probability here. Then if we go to the initial time that's 2 days earlier, and this the verification time is the same, then 4 days earlier, we now see a spreading out of the forecast, which is not surprising. Same for the other cyclones here. There's a bit of a question about whether this one up north was actually a cyclone, but sometimes some baroclinic systems tend to get into the tracker. But anyway, that's a bit of a digression. So here we see that, yeah, there's still a fairly high probability, but then after 6 days, or 6 days prior to Ian being named, that there was a very low probability based on the ensemble forecast. And then 8 days fairly low, 10 days actually it was slightly higher quantitatively. The 10-day forecast is actually a lot better than the 6-day forecast here. So what we plot, and there'll be many plots like this, but not for individual cases, is we have the lead time here from 10 days up to the verification time, which is 0, which is the time that the storm was named. And then the probability based on the ensemble is here from 0 to 100%. And so if we look at Beryl, which was a very early season hurricane last year, I think it formed at the end of June, and it was the earliest Cat 5 in the Atlantic basin on record, we see that 5 days before Beryl became Beryl, there was a 0% probability of it existing in the ensemble using the 25 knots maximum wind speed threshold from the ensemble. If we use a much more generous threshold, we'll see that some members did have some vortices in there, but just very, very weak, just like 15 to 20, but not 25 knots. But generally, the pattern sort of is evident here that the ensemble just couldn't capture it at all, and then it really ramped up the probabilities about 3 days prior to genesis. Then if we look at Debbie here, also have the orange line, meaning the AIFS ensemble, and we've got a few missing days, so ECMWF's rerunning that as we speak, and then I can complete the sample. I need to rerun all this anyway. So Debbie was an interesting case here, where there was quite a lot of optimism of a storm forming about 5 to 8 days out, and then by 3 days, oh, well, those were a lot of false alarms, maybe it's not going to form at all. And then closer to the time, oh, wait a second, this is going to form after all. So this is a pretty alarming dropout right here. And we've seen this in a few cases, a couple of cases each year. And the AIFS also has this too. So a completely different forecast system with completely different principles also had this. So our suspicion is that these dropouts are largely an issue with the initial conditions, that sometimes just the waves are not too too coherently produced in the initial conditions. Just they're very fine scale structures. The location of convection is important. It's just not captured that well. Whereas when it's spun up here with a longer lead time, then it's just sort of blissfully spinning up storms. So there is this sort of issue sometimes in a 2 to 3 day period that we've seen. Oscar was another case that was fairly jumpy here too. And so what we see in each of these cases, there's also a very strong sensitivity to this threshold value. So one has to be really careful when one's talking about a probabilistic forecast quantitatively from an ensemble, that there are very high sensitivities to how one defines the tropical cyclone at this sort of grid space. You know, many of you model at convection resolving resolutions where you really do look for the more realistic maximum wind speeds, but we're just not there yet with these global models. So here's just a summary for the overall sample of 94 cases over the last 5 years for the operational IFS ensemble. There are lots of dots, so it's essentially like those 4 storms that we had in the previous slide, but it's 94 of them now, and they're all just for the 25 knot Vmax threshold, which is a bit subjectively chosen, as many of the things in this talk are. So if we look at the longer lead times, that 0 is always the time that each of these storms is named. We look at the longer lead times, and we've got a lot of probabilities that are nearer to 0, which is not surprising. What we did find surprising, although the Beryl case and the Debbie case should probably make us less surprised, is that we have a large cluster, and the bigger dots means that there's just more cases with that particular probability. Even to 72-hour lead times, we've got a lot of the bigger dots with the lower probabilities, that it's really kind of dominated by low probability cases here, just 72 hours before the storm's named, which is very concerning because that storm could undergo rapid intensification and be like a Cat 2 hurricane just a day later. But then if we look at 72 to 48 hours here, that we see now 48 hours that it's fairly top heavy in the probabilities. So it's not this sort of nice linear increase in the probabilities that one might expect as the lead time shortens, that it's actually a fairly abrupt leap between -3 days and -2 days there. So we don't know whether that's like an intrinsic predictability issue or whether that's just a challenge with the model initialization. Here's just an example of all of the 2-day forecasts. So the reds are high chance of formation, and then this is the middle, and this is the low. So these are the same sort of scales as the hurricane center colors. And then the dots are just where they were named. So for the 2-day forecast, we see a lot of red, which is probably not that surprising. That there's a bit of yellow, especially at the higher latitudes, that there are issues with tropical transition in the forecast, or these sort of troughs that move offshore and they're really not caught well at all in the ensemble members. So we'll compare that against a 5-day forecast. We'll go back and forth. We see there's actually some regional dependence here in how the probabilities change. So look at the Caribbean. They're almost all yellow for the 5-day forecasts. The 2-day forecasts are mostly red here. And then Rosamar pointed this out, and I hadn't really noticed it before, but south of 15 north, in the eastern Atlantic, we also see that there's a lot of low probability cases there, and then by 2 days there's a lot of increased confidence. So this is all to say that there is a regional dependence in the ensemble-based probabilities. So talking about low probabilities, which is just something I'm quite interested in, they're more seldom studied compared with the more classical large African easterly waves. I subjectively call a case low probability if the tropical cyclone probability falls below 25%, 96 hours or closer to the verification. So at Beryl, as you saw, the probabilities really dropped off quickly as we marched the lead time backwards. So this counted as one of the only two cases that were subjectively determined as low probability in 2024. In 2020, there were many. There were a lot of weak waves that then surprisingly formed in the Caribbean, and many of them had Greek names because they were late season. It was a very active season. So if we look at a map of all of those cases, then here they are. And there's actually a disproportionately high number of cases in the central to western Atlantic. So I based my NSF proposal on this particular figure, and 3 reviewers really liked it and 1 didn't, but the program manager decided, okay, let's go ahead with it. So I'm not really going to talk about it here, but my goal over the next few years, and this is in collaboration with NCAR, is to look more at the physical mechanisms behind these low probability cases, especially in the Caribbean and then the Western Atlantic. And especially I think that they're more sort of convectively driven, that it's a very sort of weak and disorganized precursor disturbance. But yeah, it probably needs convection to occur just at the right place at the right time, or it may need some forcing from another system, perhaps some help from a Central American gyre, or even a jet that may be coming across Panama here may add to some cyclonic vorticity. But that's all just a hypothesis, and we've got nothing to really back that up yet. But this is the motivation for that. Okay, just looking at waves versus non-waves here. So it's an unequal sample, and the wave is just defined here by NHC in their tropical cyclone reports. So it just tells a general story here that for the tropical cyclones of non-wave origin, their probabilities are generally lower on average. And so for those of wave origin, it's not as if they're very high necessarily, but the probabilities are generally higher. That's probably the only real point I want to make there. And then the IFS ensemble underwent a pretty major resolution change between a 22 and 23 hurricane seasons. And this was a huge computational investment by ECMWF, so hopefully their probabilistic forecasts are more accurate. I'm not testing the accuracy here at all, but just showing, albeit for separate samples, that with the higher resolution, that we've generally got a higher, or the range of probabilities is generally with higher values compared with the range of probabilities with the lower resolution ensemble. The range of probabilities is also much wider for the 18-kilometer ensemble, so now the range of probabilities has narrowed just a bit. It's pretty interesting that the 25th percentile here of the 9-kilometer cases is pretty similar to the 50th percentile of the 18-kilometer cases, just sort of looking at the rankings of the probabilities there. So resolution does matter, but that does need a proper evaluation, which I haven't done. Okay, onto the AIFS here. So with these, it's a little bit mixed. They're more or less on top of each other. I gave the seminar at Colorado State yesterday, and I actually put like a circle around here to say that, well, there might be some high probabilities in the AIFS. Then another of my former PhD students, Kurt Hansen, was in the audience. He's just like, oh, the results are too ropey, don't show that. So I took the circle out here. And I think it's just such a small sample that we shouldn't really offer anything too conclusive here that you'll sort of make of this what you will, but it is a homogeneous sample. We can look at the cases individually. So if we look at this for 108-hour forecast for the AIFS, and that's where if we go back here, it's right here. So we've got quite a few more high probability cases. So this is the IFS here. Then we look at the AIFS, there's a few cases that we don't have the AIFS forecast for, so that's why the number of dots is different. But now if we look at the color of dots at the low latitudes, we see that the AIFS does have higher probabilities for those cases. But I don't really want to draw anything much more from that. But there's overall probably no real dramatic differences between the two. So just wrapping up this part of the talk, that we do see there are very wide ranges of probabilities, that for genesis there's not really one size fits all. There's a lot of sensitivity, if we want to make quantitative probabilistic predictions, to the threshold of the maximum wind speed and the resolution of the ensemble. So one needs to really calibrate whatever ensemble one has to compute probabilities out of it. This jump in probabilities was pretty interesting between a 3-day and a 2-day lead times. And then we saw quite a bit of dependence on the regions here, and David Richardson emphasized that in his paper as well. The probability is often higher for the disturbances that originate from the waves, but we did see quite a few low probability wave cases that are usually weak waves, but just all that more qualitatively for now. I didn't show it, but with that version change from 48R1 to 49R1, over the same sample in 2024, when 49R1 was still experimental, we saw minimal changes, which is good. So there shouldn't be dramatic changes just due to version upgrades. Now with the AIFS, as we mentioned with that ensemble, it's just a very tiny sample. It was just run for 2024 with a few gaps in there, but maybe some high probabilities in this particular range. So I think I'll pause there for the ensemble part before getting to the final part and see if there are any questions.
Any questions?
Hey, Sharan, do you know if the probabilities at 10 days or minus 10 days are roughly climatological probabilities?
Yeah, I'd have thought of evaluating that relative to climatology, and I think I should. I'll compute that and we'll let you know. So the climatology, of course, will change depending on the ensemble as well. So it's worth thinking about, how does one define a climatological probability? Is it a climatological probability of the actual tropical cyclones? Is that what you're thinking of? Or like
I think so. I'm
ensemble?
thinking of that the probability at some point should approach a steady value, which it looks like it does, some very low value, which is just the probability of any given disturbance becoming a tropical cyclone, not just in the model, but in nature.
In nature, yeah. Yeah, I should look at that, and I'm pretty sure a reviewer would ask that question too. Thanks.
Are the failures to be a TC because it doesn't reach 25 knots, or because the circle's kind of small and it's misplaced? Have you broken it out like that?
Yeah, that's what we need to do. That they do tend to have vortices in them, but some of them are just so weak. I haven't found too much of an issue with the placements. I did find for a couple of cases that some of them that either moved too fast or too slow just had like an anomalously high or low vortex strength associated with it. So displacement, it does come in some cases as a contribution to the probabilities. But yeah, stay tuned for low probability work over the next 5+ years. We'll be able to give more insights than what we have now.
Sharan, on the day 3 to day 2 jump, seems like a couple of days is on the order of the time it actually takes for the genesis process to happen. So is this just another way of saying that the model has all of a sudden realized that it's starting to happen, and the flatness of the probabilities before that is that it was having to anticipate something that has very difficult time doing?
Yeah, great question. Yeah, pretty similar to what Quinton and probably you, Chris, and several others have found is that about 2 days before Genesis, it does sort of seem as though the die has kind of been cast. It's like, okay, it's going. The vorticities are organizing. The convection is organizing a little around that. And yeah, beforehand, it's just working itself out, that it's fairly disorganized. So yeah, there just seems to be this sort of roughly 2-day time frame where it's just go time. Yeah, I wonder just sort of, intrinsically why that is.
Anything else before we move on to the next section?
Okay.
All right.
Yeah, let's get going. Okay. So now we're going to focus a bit more on the tracking of the waves using Quinton's tracker with a single IFS, so we're not talking about ensembles anymore, and then the single AIFS system. So we'll just look at developing waves for the last couple of years that Mark Di Maria pointed out yesterday, and he was correct that, well, we should really look at non-developing waves as well. And we do have the architecture to do that, we just haven't yet. Thanks to Quinton that we can track a lot of waves, especially in the central to eastern Atlantic. So what we're using here is what's now called Q-track, which tracks the 700 hectopascal curvature vorticity that's averaged within a radius of 600 kilometers. And so that's available on GitHub, and I'm sure that Quinton's discussed it with many of you. So what we use here is just, we compute the HRES, HRES is just the IFS, sorry, it's an alphabet soup. It's the single version of the integrated forecasting system. So ECMWF always use HRES for that sort of physics-based control member. And so we'll compare that against the AIFS for the for 10-day to 0-day forecasts of the waves. And we're only using integer day forecasts. So we'll just verify at the 0 UTC time, either at or shortly after the storm is named. So that's just largely for data management. Otherwise, wouldn't have the data available in time to give this talk. So we'll just show one case, actually a tricky case for pre-Beryl, just to show what the tracks look like in these systems using Quinton's Hofmüller diagrams. So I'll set this up just a little bit here. So the left-hand panel is the IFS forecast. The right-hand panel is the AIFS forecast. The dotted line is important. That's the initial time. Don't worry about anything above the dotted line. That's just the analysis at the previous times. What we do want to look at for this in this particular context is the difference between the initial time and the colored circles. So right now, the initial time and the verification time are the same. So we just see that there is this wave that was there in the previous analyses, and then the forecast is capturing this. But we actually, for this purpose, don't care much about this. This is a forecast of Beryl becoming a hurricane. So this is just the time that Beryl became Beryl right here. Now let's look at 1 and 2 days prior to that, so 1 day, 2 days. So the initial time is now earlier. This is the same verification time in each of these. And we see that there's still a wave that is tracked just about. For this case, there's not really much difference between the IFS or the AIFS, and I've looked at these for all of the cases, and there's not really much that's conclusive from the Hofmüllers that one can just say, oh, AIFS has more waves or more robust waves. That this is just an example, but there's not anything that really leaps out as being very different between the two. Then we look at 3 days, very weak. 4 days, not tracked at all. So neither system was able to catch this sort of weak but ultimately very high impact disturbance even 4 days before Beryl's genesis. So clearly some work to do on cases such as this. I was just lost there at 5 days or so. If we look at the other waves, we do see some consistency in the forecasts generally, which gives a few clues to like what my sort of general conclusions are about this. So we examined 19 cases that were identified as waves in the National Hurricane Center's Tropical Cyclone Report, and Quinton's tracker was able to track these in the IFS and the AIFS. And we're just considering cases at an equator of 22 north. So we'll show some different types of preliminary evaluations here. First, and it's just one slide, that it asks the question that can the HRES or the AIFS capture these waves earlier? You know, is one doing it earlier than the others? And what we're verifying against here is not genesis, but just the wave track and the wave relative variables in the ECMWF analysis at that 0 UTC time at or after when that storm is named. So the wave track is not the tropical cyclone best track. The wave is a sort of general broad area of vorticity, and a cyclone actually develops maybe a little bit sort of, it's embedded in that wave and maybe a little bit on the southern side, but we're just looking at large area integrated quantities here for this part of the talk. We'll also look at just some tracking of latitude and longitude and what those errors were. I don't have great confidence with the longer lead times, I'd say 8 to 10 days lead times, because it may be picking up the different wave. And so I've been looking at those, and sometimes there's that wave merges or just doesn't capture a wave at all. So I decided to confine this study just sort of where I sort of trusted that the wave was the wave that we want to evaluate. And so we just chose sort of where the forecasted wave was within 6 degrees of longitude of the wave track verification. For so few cases, and if we just have a couple of large errors, then that can really change the statistics, which speaks to a bit of a lack of robustness in the results. And then finally, we'll just look at a couple of snapshots and summaries of some of the wave relative variables in each of the two systems. So this is the one slide just on the number of days prior to verification that the tracked wave is in the forecast. So here are the 19 storms. This column here gives the number of days before that 0 UTC verification where one could track the wave. And so many of them are like at least, or 10 days, could be even more than 10 days that they're tracked in both the AIFS and the HRES here. This is all a little bit dominated by one storm that the HRES sort of lost 4+ days out. It's interesting in 2023 that there were a few cases where the AIFS was able to capture the wave and be tracked in Quinton's tracker a little bit earlier than the HRES. So much of this is a function of the tracker and of the resolution of the data that we're applying the tracker to. So I wouldn't put a lot of emphasis on this result. I'd just say that AIFS is not obviously worse. And then 2024, the results are much for muchness. They're very comparable to each other. Here's just an example of one case that's a fairly representative case of the two different models in the tracked waves. So on the top is the AIFS, and we've got in these different colors here the -0 to -10 day forecasts. And then these dots with these little circles around them are at that verification time. And then the solid black dots are the the verification based on the ECMWF analysis of the wave location. So this is about as good as we can get to approximate the actual wave. And so we see with the AIFS, so here are all of the forecasts, and some are a little bit too fast. One is a little bit too slow from an earlier initialization. If we look at the HRES, then they're actually a little bit to the south here, and there's one that's really sort of straggling along here from an earlier forecast. And there's a little bit more spread and maybe a little bit more jumpiness in the HRES forecast, but I need to evaluate that quantitatively with David Richardson's jumpiness metric. But we're suspecting that the HRES, the physics-based model, is just a little bit more volatile in its day-to-day tracks, whereas the AIFS tends to have a bit more temporal consistency. Okay, the next question was, did the AIFS wave track forecast perform better than the HRES? So what I call an improvement here due to AIFS is where the AIFS error is smaller than the HRES error. Just evaluating the latitudes and the longitudes, so pretty simple, just for 2 to 7 day forecasts here. So it's interesting that the AIFS consistently improves upon the latitude. Longitude, well, perhaps so, but maybe a bit less clear than the latitude. So quite a bit more green than red here, which is interesting. Then if we look at this just a little bit further and look at the mean errors of each of these against the verification. So first let's compare the latitudes here. So with the mean error, that's essentially the bias, that you want to be close to 0. So there is still some latitude bias here in the AIFS, but the sort of medium range, it's close to 0. With the physics-based HRES, they're all generally fairly biased towards the south, which is quite interesting, even as much as a degree to the south for the 6-day forecast. It's not a very big sample, it's just 16 cases, but it's interesting there's that consistency. With the longitudes, it seems that they're perhaps a little bit too slow generally over all of the cases. So a little slow and a little to the south. Then just the last result here would be, we'll look at the wave relative variable. So now we're just taking in a large disk. I only really did this in the last week, so I need to sort of run it for different radii and see see if anything pops out as conclusive. So we're just evaluating some of these variables, which are just on a 1 by 1 degree grid in this disk that's centered on the wave track coordinate. So specific humidity was interesting, I'll show you that. Wind shear was not interesting at all, because I just found that it's a fairly volatile type of variable, just at successive time steps. I'm actually not a big fan of wind shear for looking at that in a wave relative framework. I see its importance for tropical cyclones, but people yesterday at Colorado State are pointing this out too. It's an arbitrary definition of wind shear, and it's probably not that relevant to genesis. It's perhaps more worth looking at things like some parameters that are more definitively based on the African easterly jet, for example. And then also divergence and vorticity, and I'll show one from vorticity as well. So these are all evaluated against a corresponding ECMWF analysis field in this variable. So these are 2 very cherry-picked cases. So here's one from Leslie last year for the 850 hectopascal specific humidity from 6 days out through to the verification. This just shows off the AIFS a little bit, that it was very good at this. HRES wasn't too bad. There's just about a 6% difference in the 2-day forecast. And here are just the corresponding plots there of the 2 48-hour forecasts and a verifying analysis. And so just quantitatively, the AIFS looked a little bit closer to the verification, but it's not as if there are any major differences seen here in a 2-day forecast. So now if we compute within that 600-kilometer disk, the improvements, or say, asking a question, is AIFS better? Red means yes. I should probably use the same color scheme as the previous one, but anyway, here it is. Yeah, there's a lot more red than blue here. So at least for this variable at this particular time range, and we did see it for a 3 to 4 day forecast as well, that the low level relative humidity is, or sorry, specific humidity is captured better in the AIFS, perhaps just sort of through the training that, well, if all these fields sort of replicate something that happened in the past, then there's generally this sort of distribution of specific humidity. That seems to work. So that was one interesting result there. And then just looking at the 700 hectopascal relative vorticity for the Margot case, this is very cherry-picked here, and that it just so happened that the HRES forecast was a little bit overly strong in this situation. And so if we look at just the velocity fields here, we see that just a distribution, it was some interesting double vortex case here, that the AIFS actually got this, which looks similar to the verifying analysis, and this is a 5-day forecast. So that surprised me, but I need to look at these cases more properly. I mean, HRES wasn't far off, but it just seemed to want to intensify this vortex here. The verifying spot is this red dot. If we look across all of the cases, then there are more negative than positive, but it's not quite as convincing as the relative, or sorry, specific humidity. So I'm in the process of just trying to understand these cases. All I've done is just look at them and plot them, but I need to do some more detailed analysis. So let's wrap up. So the AIFS generally holds its own versus the IFS for the wave tracking, which I was a little bit surprised about, but yeah, there we are. I'm not really doing much on wave structure or convection, though, that doing some fairly general sort of variables and just the track. So it's really thinking about more synoptic scale type average metrics. It's especially useful in the 2 to 5 day predictions, which is good for operations. Just recapping that for the position variables, the AIFS latitude forecasts were less biased than the HRES, which were biased too far south. Longitude forecasts were largely similar. Need to investigate that a bit more. And then the wave relative specific humidity seems superior for the AIFS forecasts in the short range. But I have to emphasize that it's a small sample, and how we choose the cases and the threshold in a tracker and so on is pretty subjective. So this is the final slide. So I need to complete this study, hopefully this summer, do a bit more analysis, look at things also like the genesis timing, try the jumpiness metric there. That may be another metric by which the AIFS looks fairly good. And then to quantify the distributions of errors, I think the HRES has a few more extreme errors than the AIFS. And then moving on to the future and the hopeful collaboration with you is this particular NSF grant that came in January, and have a new PhD student, Gabe LaRouche, who'll be starting, and you'll all get to meet Gabe probably next summer or the year after. And yeah, he's quite a character, so yeah, you'll have fun with him. And so yeah, he and I should learn MPAS. So we don't want to rule out using WRF for this, because I think these questions are very much on the short range, that really just want to do 2 to 3 days for now, and then worry about longer timescales later. We have a particular interest in waves that are west of roughly about 50 west. So by then the Afghanistan waves have either developed into something, or the majority of them have deteriorated, that they're just much less organized. the vorticity maxima may be multiple. And so we can use a tracker that my current PhD student, Will Downs, has. So he has a paper in press, a monthly weather review, but we forgot to do the copyright form until today, so it's not out yet. But yeah, hopefully once AMS sort of has a copyright form and processes it, then you can all learn about Will's AI-based tracker. And that's good at capturing the waves all the way across the Atlantic and into the Eastern Pacific. So he evaluated against Quinton's and other trackers. And what it does actually uses NHC forecasters' subjective estimates of where the waves are, which could just be that, oh, well, we see convection here, so let's just draw a line through it. But then you have some sort of temporal continuity. So that's what he uses in the training together with ERA5. And then my other student, Alexis Wilson, has a paper that's not far behind. And so that's focusing more on the Caribbean, and especially the Caribbean low-level jet, and how when that jet weakens, then that offers an environment that may be more conducive to these weak waves forming, perhaps with some help from some other features there in the Caribbean. So stay tuned for those as well. And this will all sort of wrap into perhaps some more mechanisms-related talk than what we have here. So I'll stop there, and if there's time for questions, be glad to take any. Thank you all very much.
All right, questions from the audience? Kind of want to throw it.
One thing I noticed in the first table of results you showed for the waves was that the AIFS seems to be more consistent in its skill in how long it can track a wave, whereas is that like a real signal, or is that?
It's just a limited number of cases that, yeah, it's interesting that that jumped out at you. That I'd be conservative in saying that it's superior, but it's showing some signs there. But whether they're really significant or not, I think it needs a bigger sample. Perhaps just it's free of the physical biases, say, that the physical model may be struggling with too weak waves and they're just kept too far south. Whereas with the AIFS, it's just all trained on the RA5 that it just has whatever's variables are relevant to those wave tracks and doesn't know about a southern bias. So it might just be some physical biases there that are negatively affecting the HRES. But yeah, when I write this up, I'm not sure I want to overly draw the conclusions except to say that the AIFS is, it's not terrible and it's showing some signs of superiority.
Yeah, I think, consistency of skill is different than level of skill.
Yeah, so that's the jumpiness metric that I haven't done yet. It's pretty simple to code. So yeah, I hope to do that in the next couple of weeks. It's pretty easy. I do suspect that the AIFS will be less jumpy in having different tracks or values from initial time to initial time. But I need to test that and quantify it.
Hi, I wonder if you happen to know the AIFS uses a graph at a low resolution for 6-hour auto regression, and then addresses and undresses that with a encoder decoder. Do you know when they designed that graph, do you know if they were thinking about the scales of the tropics, or were they thinking about other scales in the architecture of that? Could you make an AIFS that's tropics oriented, maybe with a slightly finer graph in the tropics or something, and make an even better AIFS?
Oh, that's a really nice idea, and I'm very much shy to propose that. Generally being ECMWF, that they look at all global metrics, and we really think of this initially just as a kind of a parallel to the IFS and looking more at sort of synoptic scales and perhaps 500 millibar height. And tropical cyclones are not a formal priority there, so there's not too much in a way of wanting to condition models or data assimilation schemes or AI schemes in a way that, say, NOAA might want to. But yeah, I'd like to suggest that to them, just kind of a finer resolution or some way of conditioning that may involve more convectively related variables. That right now there's just like this table of variables that is just sort of very square and very standard. It would be nice if they have like a latitudinally dependent series of variables in the training. That sounds like an awesome research problem that, okay, we should write a proposal. And AI seems to be in, so yeah, might have a chance. Yeah, great idea.
Thank you so much. This is a really interesting talk. I'm just wondering if you've presented this to NHC directly and gotten perspectives. I mean, timing hasn't been the greatest for them.
Yeah, thanks for your kind words. I was supposed to present this to NHC in February. I'm sort of glad I didn't because the results were fairly immature. I'm actually presenting there on July the 2nd. So yeah, if there are no tropical cyclones out there. So that's a big asterisk on there.
No barrels. Right, yeah.
They are adopting the AIFS as sort of part of their suite of models. And I haven't asked them, though, about whether that's sort of part of their consensus for the track. So I'll ask them that. For intensity, that they'll definitely not adopt that. The AIFS is terrible for that for now.
Thank you.
Oh, we got one more.
Big throw. Big throw of the dice. Good shot.
Thank you. It's a great talk. I have one small question. It's I see that your analysis was mostly over the North Atlantic and the Pacific. By any chance, did you have the opportunity to look into other basins, like Indian Ocean, for example?
Yeah, this is purely for the North Atlantic. And a reason for that is that we just have the tracked data, the wave tracking for the North Atlantic. So it's largely that and a little bit sort of my own bias. But yeah, it would be great to extend this to the other basins. That ECMWF is evaluating the tracks for all the basins. So that result I showed at the beginning from ECMWF was all the basins combined. I forgot to mention that. Yeah, I don't see why not, especially with the probabilities. That's just based on the genesis location that I can take out of IB tracks and do that. So that should be quite easy. Yeah, thanks for the suggestion.
No problem.
All right, we're right at 3, so we'll go ahead and thank Sharan again for this great talk.
Great, thank you very much.
If for whatever reason you have more questions, we'll be hanging out way back tonight starting at 5, so please stop by and say hi and ask your really hard questions you were saving for the one-on-ones. So thanks for coming.
Thank you.